is video number 8 in the motion design playlist, which deals with dynamical problems. Motion design and application within 3D experience, which has integrated in a user-friendly way the mechanical systems experience and mechanical system design for motion problems. Now, what I'm going to be doing is a very simple problem. The purpose of this playlist, or all my playlists, is that I do simple problem that we can actually check against analytical solutions or other available solutions. If we can't get problems of this type going, trying to use motion design for a complicated problem is hopeless. So I have a mass spring damper system. The left side of the spring is attached to a fixed wall, and the right side is attached to a block, a mass, and the separation between the face of the fixed wall and the closest face of the block is 0.05 meter, which is 5 centimeters. Okay? Now, as far as the dimensions of the cube is concerned, each side is 10 centimeter, and the mass of it is assumed to be 100 kilogram. Stiffness of the spring is 2000 Newton per meter, and the damping, there is also damping present. And although the damper is not drawn here, but when we create our spring, it allows us to specify the damping coefficient, assuming that there is a damper in parallel with the spring, of course, 200 Newton second per meter. Now, this, the spring sits at unstretched length of 5 centimeter, so everything is still, and we move the block to 0.01 meter to the right, 10 centimeter to the right, and give it an initial velocity of 10 centimeter per second, or 0.1 meter per second in the right direction. So initial condition for this problem, and that's really the point of this tutorial or video, is that how do you impose initial conditions like this? And on top of that, of course, the harmonic force is acting to the block with that expression. So remember, we have initial condition both in displacement and velocity, and we also have a force that's being applied. Now, this is a classical problem that can be solved in any seen in any vibrations, elementary vibrations book. And in fact, I went to the book by Inman, and this is coming from that book, some example in the book. And notice that the analytical solution that is found there is plotted. Notice that when time is 0, the displacement is 0.01 meter as it's supposed to, and the slope of this line, the slope of this curve is translating into 0.1 meter per second. So it has a slope and it has an initial position. Of course, after a while, the harmonic oscillation will take over, and basically the steady state response will appear. This is coming from Inman's mechanical vibration. So our plan is to get this thing going in motion design and see how it compares with this. And remember, this is not the only way to do the problem. For example, the way I'm going to do it is I create a prismatic joint between the block and the wall, a prismatic joint, and solve the problem that way. But it is unnecessary to do the prismatic joint. You can just make this model, deactivate gravity, because gravity is automatically activated when you do motion design, deactivate gravity, and then solve the problem. So there are other ways of doing it. And in fact, if this block was sitting on a surface, and the surface had, for example, Coulomb damping, then you can't deactivate gravity, and you can't create a joint. You have to do it a different way. All right? So let's go ahead and do that. Here is 3D experience. First, I'm going to create the wall, fixed wall. I'm in assembly design. Okay. So insert 3D part. All right. Let's call this thing fixed wall. All right. So let's go make it. Part design. Okay. Now on that vertical plane, I will sketch that square which goes with the fixed wall, 10 centimeter by 10 centimeter. So let me make a rectangle here and dimension it. So this is going to be 0.01, 10 centimeters. And let me zoom in. And this one also 0.01. Exit and padded by 0.01. Actually 0.005. How about that? And in the other direction. So there we are. Notice that the way I'm going to do this problem, as far as the drawing is concerned, I'm going to make the block on the left side. Okay, the block is moving to the left, and the wall is on the right. So that's what I'm going to do. It's easier for me to do it that way. If this is bothering you, if you think it's too big, so actually let me make it 0.02. Really doesn't matter. That is going to be stationary. It doesn't come into the problem. Now, because I want to create later on a spring, what I'm going to do is I'll create a point on this face while I'm in this wall, fixed wall. So let me create a fixed center of gravity of that face, which is the middle of it, basically, right there. This is going to be used for the spring attachment. Good. So now we're going to insert our second part, which is the block. Insert 3D part. Let's call this thing the block. Okay, well, we can do it any way we want. For example, I can go on that same vertical plane. So let me see now. Vertical plane is which one is this? XY. Okay, sketch. Well, we can draw another square like that, or I can make it my job easier. I'm kind of lazy here. Project that face, and then add it. There. Okay, you can see that. And then exit. Exit. Okay, and then pad it by 0.01 meter, which is 10 centimeters. There we are. Why don't I change the color of that also? How about orange? Okay, good, good. Now I want to create a point right at the at this face, at the face of the block. So let me hide this. And let me hide this point, which goes with the block, with the wall. So now, while I'm in the block, so I make a point, at the centroid or at the center of gravity of that face, that's where the spring is going to go to. So I've got two of them, one for the block and the point, the other one fixed wall and the point, which isn't hiding right now. Now, let me bring this thing in the front so that you can see this. Okay. Good. Right there. There are 2 points sitting on top of each other because of the way it is. Now, what I want to do is I want to translate this thing by 0.05. There are different ways of doing this thing. You can use the compass, for example. If you want, you can use the compass and move it by a certain amount. For example, let me do that with the compass, actually. So let me hide this, hide that, and then use the compass. First, we go all the way to the assembly. If translating is easier for you, please, by all means. So I'm going to put the compass here on this face and click on that. And I want to move it by 0.05. Oh, the other way. Okay. Where is it? There. So we say OK. Close. And here's our wall. Let's put the wall out there. Just to convince you that actually it has moved by the separation is 0.05. Let's go and measure it. We're in assembly, so we go measure, tools. Translating may have been easier, but it doesn't matter. So where's the measure between these 2 points, right? There are 2 points. If I measure them, or the 2 faces, it really doesn't matter. I have the points here, so measure between this point and that point. And that better be 0.05. Yeah, good, good. Excellent. So we're going to close that. We're in business. All the way to the top. I don't need the compass here. I don't like to work with compass a lot, but anyway, this is useful sometimes. Okay, these planes are unnecessary, so let me hide them all. Hide them? Okay, good, good. Now, we're pretty much done here. There's nothing else to do. So, except for if you want to create your, to fix the fixed wall and prismatic, let me do that. So let me go engineering correction, fix. First thing I'm going to do, I will fix the wall. Fix here, fixed wall right there. And then I create a prismatic joint. Okay, so this edge, I'll use the template here, the 8th one. It doesn't matter because we're not doing anything complicated here. So this edge and that edge, this plane and that plane. Okay. And I don't need this last two boxes, so I just deleted it and say you don't want to do any contact detection. So a prismatic joint has been created right there. Very good. Okay, now we're done. So we're going to go to motion design. Motion design. As soon as it goes there, it asks you that, first of all, it put material properties on it, steel, because I did not assign anything to it. It uses the properties of steel and puts steel properties there. But I'm going to change that later on. And then it creates the joints. So just a second. The joints are created, but it will create the mechanism based on that prismatic joint. Okay, good, good. So remove this thing out of your way. A mechanism will be created. This name was given, so okay. Okay, good. Now, if you go to the global, you see that there is activity automatically assigned. So I'm going to deactivate this. Deactivate it. Okay, and if you click on the body, there's 2 of them, fixed wall which is actually does not move. So later on, so what I can do, if I double click on this, it puts the properties of steel on it, and based on the properties of steel, this is what mass it gives it. Okay, now, if you want, you can say this is a rigid massless, object, but this is not going to bother us because it's not going to move anyway, but I'll make it rigid massless object. So that takes care of this. If you go to the other one, namely the block, if you double click on the block, it tells you it put a mass of 0.008 kilogram on it. The reason is that I didn't assign properties, so it takes default properties of steel and puts it in there. But I don't want that. I want 100 kilograms. So put the cursor on this line, select it, and go override the mass properties, and I'll make it 100. That was my problem. Good. That takes care of this. Now, the other thing is that I want to give later on initial conditions to this. I want to move it by another 0.01 meter to the left. I want to do that, but we will come to that in a minute. Now, first of all, the spring. So we go to machine element, spring. This is axial spring. This is torsional spring. I have an axial spring. It says spring ends. There are different ways of doing it. The way I did it, I went with, I made a point here. So I'm going to select this point. This is one of them. And that point. Okay. Good. Huge. Okay. So bidirectional spring orientation, these dimension doesn't matter. Spring length. Now, I'm assuming that the unstretched length of the spring is 0.05. So obviously, when you move it another 0.1 meter to the left, that'll actually put some initial force in the spring, but that's okay. The free length of the spring is 0.05 meter, and there is damping here. This is elastic 0.05, and the stiffness of that spring is based on the PowerPoint slide is 2000, and there is damping, and the damping, I'm assuming it is 200. This is the same as, by the way, Newton per meter, Newton second per meter, doesn't matter. So 2000 for stiffness, 200 for damping coefficient, free length of the spring is 0.05. Everything is okay here, and we say okay. Good. So the spring is there. It's just that unfortunately it doesn't show it, but if you want, you can put the cursor on the helical spring, you can see that. Good. Now, initial conditions. So we go to, this is kind of weird the way it has been implemented here. You go to mechanism again, mechanism tab. You go and come across this fellow, initial conditions. See that? Initial conditions. Scroll all the way to the right, initial condition. You're going to select it. Okay, we have to select the marker. For the marker select, let's see what we can actually do. When we look at the parts right here, okay, the fixed wall has a marker. The block has a marker. I want to move this fellow by 0.01. So I'm going to select the marker of the block. Okay. And then I'm going to say, what is it that I want to do? I want to say both translation and translation. I want to say translation. And I want to say that in the x direction, both position and velocity, the position is another position, put down 0.06 because already there was 0.05 distance separation. Then I want to move it again by 0.01 to the left. So the position becomes 0.06. For initial velocity, 0.1. And then you say, okay. Now, this distance is still 0.05. It didn't move. But if I go to the ribbon here and say initial, let me go to the ribbon here in we're in mechanism and say initial state solve, it will move this orange block by another 0.01 meter, so that the distance becomes between the faces become the faces become 0.06. Let's try it. So initial state solve there. Okay, close. So now this distance is 0.06. It has already been moved by the amount 0.01. That's pretty much it. And in fact, the only thing I have to do is to apply that sinusoidal load. So let's go ahead and select the applied load. Applied load. It's a force, it's not a torque. Where is it applied at? It's applied at that. Remember I selected the point here. I made a point there. Okay. And I don't want it a constant, I want a function. Okay. And if you click on in the x direction, is it going in the x? Oh no. Yeah, it is in the x. X is this way, correct? Correct. You select the x direction. I don't want it to be constant. I want it to be harmonic. Okay. Independent variable is time. Dependent variable is length. Is force, not length. Force. Amplitude is 150 newtons. That's what it was. Offset is 0. Angular velocity is 10. You know what that thing is? That is this 10 right there. Not yeah. It's not angular velocity really. It's omega, driving frequency. That's what it is. That's what I meant, not angular velocity. And that's pretty much it. If you look at the plot, looks like that. This is the plot for times zero. Cosine is going to give you this. Is not going to be 0, so that should be. We have to fix it. Offset the different ways of doing it. So this should be 90. It should be 90. Let's check, because otherwise you get sine. Yeah, that's good. That's good. You gotta be careful about this thing. It doesn't matter in the steady state solution, but for transient one, it does matter. We say okay, and then we say okay. Very good. And pretty much done. We go to simulation. Oh, how many seconds do we want it? Just forgot to do that. Double click. I think we want it over 5 seconds. Okay. That's the default 5 seconds. Very good. And now run it. Wait until it says succeeded 100%. And now let's go and look at the animation. And later on, we're going to do the plot. So results, select your, select the step. This is the result. And then for animation, this will have both initial position, initial velocity, and the applied load, and it better match that graph that I had there. So let's actually run it. There we are. Okay. Now, if you want the plot, let's look at the block. X position of the block. Move this thing out of the way. Okay, so give it to me. There we are. And this better be that. Let's see, the first peak is around point maybe 045. Okay, remember, this says roughly 0.09. That's because here I have to add 0.5 to it, because this analytical solution is displacement from the equilibrium position. But the spring was initially let me see now, 0.05 away from the wall. So whatever you have here, if you add 0.05 to it, it should give you this plot. And first peak it does, because you add 0.05 to that 0.444, we get roughly 0.9. And anyway, you have to be a little bit careful. This is matching exactly that graph, except that you have to be careful. These things that they give you in vibrations book are all from equilibrium position, but what I'm plotting here is what is that? What I'm plotting here is the displacement, the coordinate of that point, the coordinate of the block, which is already 0.05 from the wall. And then on top of that, you add this fellow, and it's going to be that graph, which is shifted basically. All right, folks, good luck.